start. Thank you for joining us today. I'm Jessica Finnegan from Nullspace. Welcome to part 2 of our 3-part webinar series from RF simulation to 3D printing. Today, our webinar will highlight Fortify's sophisticated process for creating Gradient Refractive Index lenses, also known as GRIN lenses, and how they address complex challenges in both defense and commercial antenna systems. Today's presentation will be given by Phil Lambert, who is the head of application engineering at Fortify. At the end of the presentation, Phil will answer any questions that we have time for. So please post any questions throughout the duration of the presentation into the Q&A or the chat at the bottom of your Zoom screen as they come up, and we will address them at the end. And with that, I will turn the time over to Phil.
All right, thank you so much, Jessica. Hi, everybody. This is Phil Lambert from Fortify. I'm excited to be chatting with everyone today. And today we're going to be talking about how Fortify designs and manufactures our lenses. So just as a brief point of reintroduction, Fortify offers full stack design to manufacturing of RF devices. We do a lot of work on the RF design side of these devices using our expertise in 3D printing and antennas and lenses to work with you to optimize your antenna designs. We do some of that design in-house, and we also have partners like Nullspace and Iris who help us with that as well. We offer prototyping services, prototyping and testing to enable fast iteration in a closed-loop environment, and we also offer manufacturing services. Once we have developed a part that is ready to scale to manufacturing, Fortify has manufacturing capabilities in-house for low volume using our fleet of 3D printers, but we also have manufacturing partners in Europe and the Americas to help our customers scale their manufacturing of their parts into production. All right, moving on. So if you were around for the first presentation a few weeks ago, you may have seen this slide. This is the RF-specific digital workflow that Fortify uses to help our customers bring these lens concepts through design to manufacturing into the test range and gathering those test results. And in this set of webinars, we are following this specific case study. This is a patch-fed lens, axially aligned connector, the low vis-war, and an overall small form factor. And this is the design that Daniel and I decided would be a great point of reference for our customers and for the audience here to understand how this process works. From the design all the way through to collecting test and measurement data. So moving forward, I'm going to spend a little bit of time talking about our manufacturing platform, how our printers work, and a little bit of the specification behind there, and we'll just dive into that immediately. Okay, so Fortify uses a type of technology called DLP. For folks who are familiar with 3D printing, that's a familiar acronym. For those who aren't, that stands for digital light processing. That's a technology where UV light is projected to cure layers of photocurable resin. Our printers are designed in-house, and they're designed with a build envelope of about 8 by 4.5 by 13 inches. So we can print a solid something or a latticed something as big as about a shoebox, if you wanted to think about it from something a little bit more tangible in your life. And we have a pixel resolution. The smallest pixel that we can print, the smallest image that we can project is 75 microns. And we use a layer thickness of about 75 microns in most of our RF applications, so the machine's a lot more flexible than that. One important thing to highlight from this list here is that this machine can go into offline and sensitive areas with no internet connectivity for some of our customers who operate in the defense and government spaces. So moving on from there, I just wanted to briefly highlight a little bit of the technology that is digital light projection. It's quite literally a projector. So we have a projector that you might find in a classroom or in a movie theater that is projecting 2D images of light. And that however we shape that light digitally gets projected into this vat of photopolymer resin. Wherever that image strikes the resin, that resin cross-links to form a solid. And so what we do is we project that image over and over again as we iteratively step our layer height our build plate height higher and higher. And so one layer in our process looks like the images that I have on the screen here. Starting on the left our build plate plunges into our vat of photopolymer resin, and that build plate plunges until it's just one layer high above our glass substrate here. And then we illuminate with our digital projector to create a cross-section of our image in our photokillable resin. So we can see just a little sliver of our resin there. That's one layer's worth of resin that gets cross-linked in a shape. And then we peel that cured shape off of the film that sits in between the build plate and the glass. And then resin flows back into that interstitial space to repopulate that area with uncured resin. And then we repeat, except this time we plunge again 2 layers above the glass. So now we're selectively curing a new layer of material onto the previously cured layer. So that's how this technology works. We didn't invent this technology. This is a type of 3D printing that has been used across industry for several years now. However, what's unique in our technology is that we print with fiber-filled resins, which means that all of the photo-curing resins that we use are filled with some sort of fiber, particle, solid additive that we need to maintain the homogeneity and the distribution of those particles in our resin so that our final material properties and our processing characteristics are the same from the start to the finish of a print. And we do that in part due to a technology on our machine called continuous kinetic mixing. So continuous kinetic mixing is a module that continuously pumps using peristaltic pumping our resin through our reservoir through a circulation agitator where the material goes to get mixed and heated and then redistributed back into our print reservoir. And so this material is constantly moving, constantly getting heated if that specific type of resin requires heating, so that we are constantly making sure that our resin is homogeneous from the start of our print to the end of our print. And this technology is essential for many of our resins to be processed and to maintain the final part properties that you need for your application. So just to give you a point of reference of how thick some of these materials can be is when you add fibers, fibers tend to introduce the final part behavior that you're interested in having. The more fibers you add, you tend to impact the viscosity in a pretty dramatic way. And viscosity is sometimes manifested here in this image as thick material. I should say it always is. Rheology is also plays a role here where these materials can introduce non-Newtonian behaviors depending on the particle package, depending on the size and morphology of those particles, the content. Anyways, the point here is that these resins, these fiber-filled resins tend to get quite thick, and we need to have technology to process them, and that's where Fortify is innovated. So just to give you a point of reference for how these prints might look, I took a time lapse of a 330 millimeter tall portion of a lens. This took over the weekend to print, and say probably 60 or so hours to print this part. And you can see that build plate's moving up and down periodically. You can see the wiper moving periodically as well. What the wiper does is help to maintain optical clarity in our light path so that there's no obfuscation of our light path due to particles or any type of sedimentation that might occur. And you can see here this lens portion, like I said, 330 millimeters tall. So, 3D Fortify, we use this DLP technology for a variety of reasons. One reason is that every single layer is projected all at once, which means that you can take advantage of parallelization. So on the left, you're looking at our printer printing 5 about tennis ball sized lenses simultaneously, because whether or not you have 1 lens or 5 lenses on the build platform, you're going to project all at once no matter what. And we can take advantage of that. So we have a throughput about 5x of a desktop FDM 3D printer, just as a point of reference to show you that parallelization that happens in DLP helps our customers to realize production scale manufacturing throughput. All right, so I'm going to step into lenses out of the world of discrete 3D printing technology and into how we apply that into lens manufacturing. So one thing I do want to start here is say that we are not the inventors of lenses. In fact, lenses have been used for a long time in microwave devices. However, these microwave device style lenses are what we call constant K, or they're solid. And what you are doing is you're designing lens, or these lenses are designed to operate in a way that optical lenses are typically designed, taking advantage of the refraction that occurs between two media. You might see that, in your glasses, or how I like to think about it is if you're looking into a lake or some water and you see an object that is slightly in a different position than you'd expect it to be, and you're getting a lot of reflection from the sunlight. Same type of thing is happening here, where you're taking advantage of the shape of the lens, you're taking advantage of the refraction that occurs to that medium, and bending your waves. And so what you're seeing here are a few different materials being used. Rexolite is a very commonly used solid dielectric for lensing. Also uses PTFE, Teflon. There's a couple other specialty materials that folks have been using for microwave devices, for microwave lenses. But what we're doing is something called Gradient Refractive Index lensing. So that is a slightly different from solid lensing, and where we are tailoring the dielectric constant across a device by locally mixing air with our dielectric to create effective media. And by controlling that volume fraction of air using our latticing geometry, we're able to create smooth gradients of dielectric, or tailored gradients of dielectric across a device. And so what you're looking at here is an example of a Lundberg lens. You can see the distribution we designed here. So this would be along the radius of this lens, you can see the dielectric constant ranges from 2 to about 1.2. And here you can see that represented as a set of shells in null space. And then over here, you can see a cross-section of this lens as represented by a series of our periodic structure that I'll talk about in a few minutes. And so there have been a variety of these devices manufactured over the years. However, historically, these manufacturing technologies have been very challenging to scale. Fundamentally, they're all doing the same thing, which is they're trying to mix in air either through a foaming technology or through perforated substrates. And what you're looking at here are drilled laminates that are then glued together. And so these technologies, they require significant amount of manual labor, significant amount of manufacturing time. And the result is we haven't really seen any of these technologies scale to manufacturing, especially as you get to higher frequencies. I will say there has been one company that has managed to make a business out of lensing, and that's Matsing, and that they use an artificial magnetodielectric. So if you're ever in a stadium or at a music festival and you see a big ball floating around somewhere, that is a Lundberg lens that is most likely manufactured by this organization called Matsing using an artificial magnetodielectric. Those tend to be lower frequencies, which is why they're so large. But if you look at the landscape of 3D printing, this is a rich academic area of study. Folks have been studying this for years now, trying to get to these effective dielectrics to create lenses. However, if you look at all the different types of polymer manufacturing technologies folks have been using, the most common that we tend to see is this filament extrusion technology. So like your desktop FDM or FFF 3D printers, Z-Morph, Enders, those types of things. You tend to be able to process decent materials with those. Thermoplastics tend to be excellent dielectrics. They tend to have good resolution, right? You can switch out those nozzles. You can get to really, really fine features, sufficiently sub-wavelength, but there is a trade-off between throughput and resolution. If you want things to print quickly in FDM or FFF, you tend to need to sacrifice with resolution. Photopolymer jetting and vat polymerization technologies like SLA and DLP tend to have great resolution and throughput, but the dielectric materials historically have been inadequate for anything and having semblance of a high performance GRIN lens. And so that's where Fortify fits into this niche really well. We offer DLP 3D printing technology with great resolution and great throughput. Now we're offering excellent dielectrics for this technology as well. And so I did a brief materials landscape to give folks a general understanding of where these materials sit on this chart here. On the right side of this chart, where dissipation factor tends to be a little bit higher, are those thermoset materials, those photopolymer curing materials used in technologies like SLA or DLP or polyjet. And on the left side, you tend to find our thermoplastic materials like our Altems, our PCABSs. Those tend to have better dissipation factor, very critical behavior for our dielectrics. But like I said, they tend to suffer from throughput and resolution limitations and trade-offs. And if I just added some of those classic microwave dielectric materials, Rexolite, HDPE, or Teflon, PTFE, they kind of fall off this chart. They're so low loss, very low dielectric constant as well. So interesting materials, but not yet 3D printable on a scale that is meaningful for production applications. So what materials do we work with? Well, Fortify offers 4 materials right now that fit into this landscape. On the top, we have our sintered ceramics. Our most commonly used sintered ceramic is alumina. It's a 97% pure alumina that gets sintered at 1750 Celsius. Tend to have operation temperature somewhere in the 14 to 1500, depending on what type of thermal environment you're exposing it to. And then on the right side, we have a newer emerging material called LSAS. It has a dielectric constant of around 5.6. Definitely gets centered at a lower temperature. It has some silica in there as well. Pretty decent material. Might consider it for, pretty decent insulator. It could consider it for lower temperature, leading edges, different types of things that would protect radio frequency components. On the bottom side of this slide are our low loss printable polymer dielectrics. So these 2 materials are from Rogers Corporation. The one on the left, if you've ever seen Fortify present or talk about our technology, if you've ever visited a trade show booth, you might have seen this material, Radix 2.8. That has a dielectric constant of 2.8 and a loss tangent 0043. We use this a lot for Lüneburg specific designs just because it's got a perfect dielectric distribution, perfect dielectric constant to get to the dielectric distribution using our effective media approach. But on the right, if you're interested in things more exotic, you can do quasi-transformation optics style designs or optimized lens designs using this Radix 4.6 material with a dielectric constant of 4.65. Similar loss as the Radix 2.8. And yeah, like we're using that material. That is a little bit earlier in development. It's available now, but it's not yet to a production stage. And we're using that for all different types of things, including things like field of view enhancing devices. Okay, moving on from that. I'm going to briefly talk about polymer composites and go into some details there. Just digging into the Radix 2.8 for just a second. Like I said, this is a material that's in production now. We use it for a lot of our devices that we manufacture. Our customers are getting a lot of value out of this. Has a dielectric constant of 2.8, dissipation factor of 0043 when characterized at 10 gigahertz, and very important, very low moisture absorption. If you're making dielectric lenses and you start to uptake moisture, you're going to start to really impact performance. So that moisture absorption, while it's not a primary characteristic, is really critical for our Lüneburg lenses. And these materials are best suited for applications exhibiting temp ranges up to 80 C. So not a super exotic, not a super high thermal stability material. But excellent for a large variety of applications. And when you look at this material's behavior across frequency, it's very stable. We've characterized this using microstrip differential phase method. And you can see from 5 gigahertz up to 50 gigahertz, very, very little change in the dielectric constant cross frequency. So you can have a lot of confidence in this material being very stable when you're doing wideband lensing. And just to quickly touch on these materials once again, the material on the left is the Radix 4.6, dielectric constant of 4.65 and a loss tangent of 0032 in development, available for prototyping right now. And on the right, we have our sintered alumina material, which has a dielectric constant of 8 and a very low loss tangent of 0002. This material also earlier in our production pipeline, but available for doing all different types of lensing applications. And I'll show you how we do it in a little bit. So taking into mind these material characteristics and how it falls onto this materials chart here. Again, we have our thermosets on the right and our thermoplastics on the left, where our thermosets are higher loss, our thermoplastics tend to be lower loss. You can see where these non-printed microwave materials fall into this chart, and then Fortify added to the mix. So we've got Radix, really competitive down here with the 2.8 and very low loss. Only thermoplastic, only thermoset that sits to the left of this chart. And then we have the Radix 4.6, a little bit more interesting in many ways because it's kind of breaking that mold of, the 3 to 4, the 2 to 4 dielectric constant range that you might see from typical polymers. Now we have specialty polymers. We're kind of breaking that mold and getting up to higher dielectric constants. And then the ceramics just are generally in a league of their own as far as characteristics. quite low loss, and definitely the alumina, can't even fit it on the chart here, sitting up at 8 dielectric constant and 0002 loss tangent. So very interesting materials. And we use these materials to do lensing. And so we do our lensing using this technology, using this type of architecture called a gyroid. Periodic lattice structure in a family of triply periodic minimal surfaces. So the gyroid is this undulating surface-based lattice type design that is self-supporting, and it's got these internal channels that go all the way through these devices. And we like it for a variety of reasons. It's great to 3D print. Actually, I have a slide on that, so I'll hold off right there for a second. And what we do here is we control the air fraction of this device, of this unit cell, by controlling the wall thickness. And by controlling the wall thickness and thus controlling the air fraction, we can thus control the effective permittivity. And I'll go into that in a follow-up slide. So there are some features about this unit cell that are very important to Fortify. The features of this unit cell are the overall size of the unit cell, but also the wall thickness, which is thickness of these undulating surfaces here, and then the resultant pore size. And so we pay very close attention to the pore size and the wall thickness of our unit cells, because those generate the limits in our effective media. How thick of a wall we can print represents how high of a dielectric constant we can achieve. And how small of a pore we can print and clean represents how also that same limit. So let's look at a chart here. I think it'll tell that story a little bit more clearly. So here we have the cross section of a lens, and we have our gyroid unit cell here. The walls are very thin, the pores are quite big, and we are realizing a very low effective dielectric constant. But as we go to thicker walls and smaller pores, we get to a higher dielectric constant. Now, if you bring that concept onto a chart, where on the x-axis we have effective permittivity, and on the y-axis we have wall thickness and air fraction. We look at the wall thickness of our gyroid in this blue line here. As our wall thickness goes up, our effective permittivity goes up, and that's because the wall thickness controls our air fraction. So as the wall thickness goes up, we can also see that our air fraction line, this black line, goes down, and our effective permittivity goes up. Therefore, to summarize, the more material you have in your unit cell, the higher your effective permittivity is going to be. But we have limits here. We have manufacturing limits. Our manufacturing limits are how thin of a wall I can print, and that is represented here. I can't go down to air because I can't print an infinitesimally thin wall, and so I'm limited at some point. And then I can't print an incredibly teeny pore. I have to clean those pores out, and I have to have access to clean those pores out. And so we are limited in terms of effective permittivity ranges we can achieve by the geometry of this unit cell. But we do like it, and we like it for its printability. These unit cells tend to be very self-supporting and ideal to 3D printing for its shape. The mechanics of these unit cells are very excellent. When compared to other strut or truss-based unit cells, these are much more robust, and they're isotropic. And so long as that unit cell is fairly small relative to its frequency, the isotropy of that device is incredibly high. All right, just to quickly touch on that a little bit more, we have our gyroid unit cell here. We're going to identify this feature, which is the size of that gyroid, or one axis length of that gyroid is lambda guided. LG here. And so if we look very closely at our gyroid, we can see that it is actually represented by an octet periodic structure that is translated and rotated to create every single octet of this geometry. And we're going to call that LG over 2. And so we have this unit cell constant that we're calling LUC here. So that unit cell constant LG over 2. And so long as you maintain a rule of thumb representation of this unit cell equal to 0.5 of the wavelength of your frequency when it's guided within that dielectric, you will have a nearly perfect effective medium. And so here's the way you would read that. So on this table here, if you look at your unit cell size, and so long as that unit cell size is 0.5 your guided wavelength, then you will have an effective cutoff frequency in this column here. And so for the host dielectric of 2.8, which is a radix 2.8, the unit cell size of say 5 millimeters, you can come and follow this and see, okay, we expect this 5 millimeter unit cell to operate pretty perfectly up until about 35, 36 gigahertz. If we wanted to go lower frequency, we could tolerate a higher unit cell size. All right, and we characterized this using this test method here, where we created four Lundberg lenses of different unit cell sizes, but of the same exact diameter, and so it should have the same exact gain. And we could see and we measured it across frequency to see where the gain started to drop off as a function of these unit cell sizes. And you can see the 5 millimeter unit cell performs admirably up to 40, but as we get to larger and larger unit cell sizes, our gain starts to taper off, and then at 12.5, we can see we barely make it to 20 gigahertz. So just as a point of verification, we've done quite a bit more verification than that. We've also looked at the simulation analysis using eigenmode solver and creating dispersion diagrams to find out which modes exist at which frequencies for our unit cells. I won't pretend to be an expert in this. My RF antenna engineer on my team has been studying this a lot in depth, but I will let you know that all of our simulation is aligning with our rule of thumb that we generated with University of Notre Dame, who did a lot of that work on a few previous slides. And so how to digest all this? We created this material selection guide to help you to understand what effective dielectrics are available to you across which materials, depending on unit cell size. So the way that you do this is you determine in your application, what frequency am I trying to design my lens for? Okay, it's maybe 40 gigahertz, 35 gigahertz. You say, okay, which materials do I need? What kind of dielectric constant range do I need in order to accomplish my design? You'd say, okay, I can do it in just 2.8. So you then come over here, you'd say, okay, I know I can use a 5 millimeter unit cell. And on my y-axis here, I have effective permittivity. We can go from about 1.2 up to 2 point something, 2.4 probably. And that's how you'd read that. And we also have it for the radix 4.65, and we also have it for the aluminum material, both of which are still under development. So I expect these maps to shift a little bit over time. So just zeroing in really closely on the 2.8 for just a second, because this is the material we use in the design with null space and Daniel. And so we would just look real close here, unit cell size based off of my 0.5 lambda guided. We know it's going to be about 6 millimeter unit cell. And so this is my dielectric range that I can print, these upper and lower bounds are, of course, controlled by the pore size and the minimum wall thickness I can print on the printer using this material. Always, we have the solid material available to us, which is a dielectric constant 2.8. So there you go. That's your design space that you can use for your application or for your lens. Okay, so applying this in practice, we're going to quickly look at a repeatability experiment that Fortify ran using a tennis ball sized Lundberg lens, 6 millimeter gyroids with a dielectric gradient of about 2 to 1.25 simulated. And then we ran an experiment where we took this lens and we put it into a fixture in front of a WR42 waveguide. And then we turned it into 4 different directions. So we measured it from 4 different orientations of the device and effectively 4 different orientations of that unit cell to look at repeatability in our manufacturing process, but also in our design. And the results were great. So we had 95% manufacturing yield. And what we're doing here is just measuring bore site gain. So we don't have a chamber that allows us to create complex beam patterns. So we're just looking at bore site gain on our VNA and measuring that across 4 different positions on each lens across 19 lenses. So it ends up being 76 gain measurements. And across all 76 gain measurements, we saw a standard deviation of 0.06 dBi with a maximum deviation of about 0.2 dBi. So from our perspective and from our customers' perspectives, that's very repeatable. So we're very happy with that result. So taking all these concepts and all these design criteria, let's briefly talk about how we go about designing these lenses. I'm not going to take it, I'm not going to tell you in this webinar how we go about designing the dielectric distributions themselves. I'm going to save that for Daniel in the following webinars. I'm going to pick us up here at the effective permittivity portion of this workflow to talk about how we interface with dielectric information and convert it into printable geometries. Okay, so there are a few ways that dielectric information can come to Fortify. One is a shell-based dielectric profile, and so instead of taking full advantage of arbitrary tailored dielectrics, you can stick with more traditional shell-based dielectrics. They tend to be a little bit easier to design and simulate. And so in this case, what we're looking at is a stepped design. So we've got the shells distribution with 13 shells with a dielectric constant minimum of 1.25, and you can see that here. And you can see how this distribution, the shell-based distribution overlaps with more of a pure Lundberg style distribution. This lens was printed in 2 halves and assembled. But Fortify can also read in point cloud designs. So if you wanted to take advantage of arbitrary point clouds, where each point represents a dielectric constant in 3D space, we can read that in. And so what you're looking at here is a point cloud still representing a Lundberg style distribution, but the heat map that you can kind of see through this point cloud shows you that the core is a lot higher dielectric constant than the surface. This allows us to get a lot more flexible in our designs using more of a voxel-based approach if you have the capability to do that optimization, and Nullspace will show you how to do that in the following webinars. And we also have automatic support generation. Let me just show you that really quickly in our tool set called Gradient that we use to design these lenses, which is really fascinating because it saves a ton of time. You can see it happening here. Just watch this for a second. There we go. And so each of these points that are being highlighted here would be a location for a support to be built. So an excellent technology that we have developed at Fortify. And so one important thing I want to make sure people take away from this is that we cannot print 1. We can't print a dielectric constant of 1. So it has to be above 1, and it has to be within the bounds of our dielectric map that I was showing you just a moment ago, which is why there's that drop down here at the end of our dielectric constant curve. So 1.25 tends to be pretty common in our designs as a minimum dielectric constant. We also have a part size limitation, which we spoke about earlier, but here it is represented. 330 by 220 by 112. That's the maximum part size we can 3D print on our printers. All right, talking very briefly about very large lens printing. How do we get beyond our print volume to make things that are very large? You might want to go very large if you want a device that creates a lot of gain, or you might want to be, print very large if you have a very low, much lower frequency type of lens than say a Ka band. If you want to go to X band or lower than that, you might need to go to large devices. And so Fortify has established and developed some technologies and workflows for printing segments of lenses, and then using classic carpentry joining and adhesives to glue those lenses together. We've done a lot of verification and validation of this. We know it works. I don't have time today to cover the details there, but I just wanted to show you a couple of the different types of alignment features and joining features that we use to get to larger devices. So this is something we did recently where we did a bow tie joint for final fixation, and we're really excited about that. Here's an example of when we apply these to a lens. And so we designed a 13-inch diameter lens with an organization called Southwest Research Institute. And they did some computational design to create this large lens. Fortify segmented it into 6 pieces, which you can see here. Here's one piece printed here. This was assembled and then attached to a device at the bottom here to mount 5 waveguide feeds. And then that was fed to generate a high gain lens for low power, low complexity wideband apertures. These are really interesting because it represents a type of architecture called a switched beam antenna, and you might use those relative instead of a phased array lens if your application can tolerate fixed beam positions rather than the sort of arbitrary beam positioning that a phased array can achieve. And the trade-off there from the positive side is that you don't need to use phase shifters. You can reduce your number of amplifiers, and then fewer active elements means lower power consumption, lower heat generation, reduced operational cost. And so our customers using these in direction finding applications, ground to air, satellite communication, cellular base stations, all types of places. So switch beam antenna is a really interesting application that this large lens tends to fit well into. Okay, so we talked about large lenses, but how do we go about combining different dielectrics to expand that dielectric range you can achieve within one device? And so you saw this chart a little bit earlier. And say if we wanted to take advantage of the radix 2.8, which has a lowest dielectric constant, as low as 1.2, say, but we also wanted to take advantage of the high alumina, which we know has an effective dielectric constant of around 5. The dielectric constant of the solid material is around 8, but we can achieve around 5 to 6 using our effective media approaches. And so that means we want to go from, say, 1.2 to 5. We can't do that on one material, so we have to start looking at hybrid designs. And here's a great example of some work we did at the University of Notre Dame, where if we looked at that switch beam antenna lens, we had a compression ratio where the max dielectric constant and the compression ratio is about 1. But if we go to if we introduce a maximum dielectric constant of around 6, we can compress it by 5 to 6x in one axis. And so that means we can get to much lower form factors by leveraging all the phase change that happens in those higher dielectric constant materials. And what we had to do is make sure we had an overlap zone of dielectric constants, so we had a smooth gradient from within that design. And so this is what the result of that design was: multifunction ultra wideband antenna coverage via lensing for Class 1 or Class 2 UAVs. That's the application for this lens. It's a hybrid lens for a switch beam architecture, very similar to the one I was describing before, that covers 2 to 40 gigahertz, so super wideband, and it takes advantage of combining those dielectric materials together to create a high gain, fairly low scan loss, low profile antenna lens system. Okay, Fortify is also working on antenna integration. It is a 3D printing technology, which means you can print all different types of features attached to these devices, but it have to be out of the same dielectric material. And so here are a couple of examples of how we've designed some little fixtures and tabs that mate with an antenna that you're trying to test this device with. We've also designed a couple other things here, different types of antenna mounts, and we have some heat set brass inserts into the back of this antenna lens here. We can 3D print these lugs and threaded inserts here. And then here's a device we designed recently with Iris, where the Fortify component has mating fixtures and an integrated radome. So very interesting. What I want you to take away from the slide is that when you're designing the lenses, you can think beyond. You can think about how you might integrate this device in your lens system. And we can 3D print those features directly onto the device to be integrated in later. Okay, so here's an example of how this was used. Here's an example of a quadridge horn that was feeding a lens. You can see those mounting tabs right there. This lens was interesting because it increased the gain significantly of this horn up at the higher frequencies, up to 8 dB. So exciting. These devices tend to be used in test and measurement systems. Okay, Fortify is also continuing to push the limits, because as you saw in those charts where the dielectric constant range was limited up at the higher frequencies, we've done an experiment recently where we were really trying to push that to demonstrate that we can indeed manufacture lenses that operate from 60 to 71 gigahertz. And here's a 2-inch Lumberg lens design where we used a unit cell of 2.8 millimeters, so very small, with a minimum dielectric constant of that surface of 1.38. We did some full wave simulation on that. We fed that with a WR28 waveguide, and in simulation optimized the feed distance for peak gain. And here are the results. On the left, you're seeing our measured performance where the directivity is in the green, so about just above 29 dBi for this device. And you see the gain drop off pretty significantly above 70 gigahertz. That's correlated to the cutoff frequency for that unit cell at that frequency. So we had expected that there. And here is the simulation of the material in our full wave simulation. So pretty similar performance up to about 70, 71, where we start to see that tapering a little bit. Okay. Just want to quickly touch on how we apply this technology to phased arrays. Fortify and Rogers Corporation co-developed a field of view enhancing antenna. Sorry, I'm going a little bit faster because I'm running out of time. We developed a field of view enhancing antenna for a phased array. And this helps to achieve complete coverage over a region that you're trying to cover with a phased array with fewer antennas by increasing the field of view of an antenna from, say, 120 degree sectors to 180 degree sectors. You obviously need fewer antennas to cover the same amount of area. And you might find this in fixed wireless access or radar or EW applications. Anywhere you might find a phased array doing things, you can reduce the number of phased arrays that you need by introducing a field of view enhancing lens that will take your phased array that typically has a field of view, typical phased arrays tend to have a field of view of plus or minus 60 from boresight. By introducing this lens, you can take that 60-degree beam and bend it out to 90 degrees. And so here's a brief view of what that looks like. Here's the distribution of that lens. In this example, we're only steering in azimuth. And so we only are looking at the azimuthal steering of this device. And you can see what those E-field simulations look like when the phase and amplitude are changed to create these beams that point out. So long as you have aperture off at your most dramatic angle, you can create a lens that generates enough phase change to bend your beams to point out to 90 degrees. So you can see that happening here. On the left, you're looking at this phased array, nominal behavior, which is a phased array from Anoki Wave, their development kit, their innovator kit. And you can see this black line is generally where their behavior starts to fall off. So around a gain of around 60, sorry, a beam pointing at about 60 degrees here. And then with our field of view enhancing lens, you can see that's that black line right there is the phased array without the lens behavior. You can see that we've got some beams here at 80, 85 degrees from boresight. So using this device, we can create beams that point out to 85, 90 degrees to help to reduce the need for as many phased array units deployed to a field to cover the same type of area. All right. So now, quickly closing off with the fabrication of our test vehicle in this webinar series, just revisiting it for a second, patch-fed GRIN lens, designed by Daniel at Nullspace. And Daniel provided me with this dielectric distribution. So we've got 4 permittivity regions. One is 2.8, so solid radix, 2.26, 1.78, 1.36, those 3 following rings. And Daniel said, this is operating between 15 and 7 gigahertz. And so I looked at my map of rule of thumb frequency cutoffs. And I said, a 6 millimeter unit cell is going to be pretty good for this. And that gives me a cutoff frequency of around 30, plenty margin of safety there. And then I went to look at my 6 millimeter unit cell dielectric effective permittivity map and saw that, we saw that we can design a lens from 1.24 up to 2.37. Looking back at Daniel's dielectric ranges for those 3 effective permittivity regions, we felt really confident that we could design this device using this design. So I didn't have to go back and tell Daniel to redesign it. So that was good. So we had the part design that came in as a solid body with 1, 2, 3, 4 regions. And then I brought that into our design tool and created our gyroid architecture, as you can see it here, with a lower dielectric constant being at the surface and the solid core being right at the middle. Then I had to prepare our build, which was putting 2 builds on the platform, slicing it, creating our print file, bringing it over to our 3D printer, and printing it. Now, since this is a liquid-based resin process, that means we had our pores filled with uncured manufacturing material that we then have to clean out. So we clean that out using a series of solvent washes and compressed air to get all of that resin out. And then once it's fully clean, we bring it to a UV and thermal bake to finalize the cure and bring it to a final state of manufacture. So that's the final part. And so that's so this is the device that Daniel in the following webinars will discuss the front end design and the back end test and measurement, so that you have the full story for this specific design. So just want to end by saying thank you very much for listening. My name, once again, is Philip Lambert. I am the head of applications engineering at Fortify. You can reach me at this email address, and then we'll leave it at that. Jessica, I think I'm ready to take some questions.
Okay, thank you, Phil. We have a few questions. If anyone has more questions, please just put them into the Q&A or the chat, and we have a few minutes, and I think I can get to some of those. Okay, let's start. Let's see. The first question is, what limits the bandwidth of your lenses devices?
Yeah, what limits the bandwidth? Yeah, so that's a great question. Just to revisit so there are two ends of that, right? There's the low end of your bandwidth and your high end of your bandwidth. On the low end of a lens, you tend to need some multiple of your free space wavelength in order to do something interesting using a lens. Lundberg lenses, for decent gain tend to be 4, 5, 6x wavelength. And so that tends to drive the overall size of your device. So that limits your lower bandwidth. Sorry, the lower end of your band. On the high end of your band, you're limited by the resolution of the printing process as it relates to the unit cell size that you need to select. So we have our frequency cutoffs using our effective media. And if you were to take a look at that 70 gigahertz example I gave, the bandwidth is limited on the high end by the smallest unit cell size I can manufacture, and then the effective dielectric range associated with that. So on the high end, we're limited by unit cell size. And on the low end, we're limited by device size. That tends to be how we think about the bandwidth of a specific device.
Great, thank you. Hopefully that answered the question. And then we have another one. Can you provide more information on how to model a parametric gyroid unit cells? Do you provide software?
So Fortify does that design for you. Our customers tend to be RF engineers or antenna engineers who are excellent at coming up with concepts related to antennas and lenses. And that's where Fortify wanted to make sure that we were in a position to support. So we have the software needed to read in your designs to create the effective permittivity. So you are not responsible for generating the gyroid designs. All you need to provide to Fortify is your dielectric distribution, and we can take care of the rest from there.
Okay, then we have a follow-up from that. Can you print other unit cells beyond a gyroid?
Yes, that's a great question. At the end of the day, this is a 3D printing technology. We can print anything that is printable, including a wide range of unit cell geometries. Some of our customers have come to us with unit cells that they have experience with in other 3D printing technologies, and we welcome them to come to us with those designs, and we can print them. We really like the gyroid because we really understand it from a manufacturing standpoint, from a mechanical standpoint, and from a radio frequency standpoint. And we know it's going to work. We know it's going to work every time. And so that's why we really like the gyroid. But yeah, it's a 3D printing technology, and we can print any number of unit cells. I will add that some unit cells, we are exploring other unit cells, and there are some advantages to be had of some of the strut and node types of architectures. You can tend to squeeze out a little bit more on the low end of that range because they tend to be less relatively dense than the gyroid, but the trade-off tends to be fragility. So the gyroid unit cell is a great, solid, robust unit cell that offers a lot of flexibility while also being a nice, mechanically robust unit cell.
Great. I think we have time for a few more questions. So if anyone has more questions, just put them in the Q&A. Let's see, we have some more. How have you validated the gyroid unit cell?
Yeah, excellent question. We have done quite a bit of empirical testing and simulation to understand the gyroid and understand its limits. As you saw in the repeatability testing that we did, that was just a small experiment that we ran in-house using our manufacturing equipment in our small test lab. And empirically, that provides us with the confidence that gyroid unit cell is effectively doing what we think it's doing. And it matches simulation as well. We've run through a number of other device designs with some of our partners and customers. And what we tend to find is that the gyroid's performance as a lens matches the simulated performance in every case. The area where things start to break down is as you start to get closer and closer to your cutoff frequency. So as you try to squeeze out just that last little bit of performance up at the upper frequencies, you have to keep your eye on the cutoff there. We've also done quite a bit of just gyroid simulation, looking at it from a bunch of different angles. We've also done some characterization and waveguides, looking at the empirical measured data of effective coupon samples. So we create these small samples of the gyroid at a constant dielectric of the lattice geometry and measure its coefficient of transmittance and coefficient of reflection. And from that, we extract the effective dielectric constant. We verified that against simulation. And so we have a really solid and really confident understanding of the relationship between these effective media and their simulated performance. And so through a variety of ways, we've validated it, and we know it will work.
And then we have one question that kind of builds off that, going back to the lenses. Like, how are you verifying their performance?
Yeah, same type of thing. Our workflow establishes first a simulated performance in tools like nullspace to have a good understanding of the device. And then in some circumstances, we'll go as far as creating the gyroid geometry and creating a mesh out of it, and then bringing that gyroid back into the simulation tool to create a simulated gyroided lens geometry. And so from there, we manufacture and then we test. And in those tests, we always compare back to simulation to verify the expected performance. And when we don't understand what's going on, we always do some optimization, either in the test and measurement setup or in the design setup, until those two behaviors converge. And then we have full confidence that we understand the lens and that we verified its performance in an antenna system.
Okay, thank you. Those are all of our questions. And thank you, Phil, for presenting. And we hope to see everyone on part 3 on July 10th for the EM simulation with cylindrical GRIN lens design. And Daniel will be hosting that one. But thank you, everyone, for coming. We really appreciate it. Thanks, Phil.
All right, thanks, Jessica.
Okay.